So now what we are discussing is about the noiseless coding theorem, right? So that's what where we start. So what is that? We just recollect what we discussed and then we go for today's class, right? So what we discussed was we have the distinct symbols available in the right, the symbols available, and we have this probability associated with that, like 0.5, 0.25, and then point, say for example 125, and say this is 0.125, right? So when you add this probability, it is ending up with 1, and you are going to use the symbol D, right? Either 1, it is like this. You such a way that is, first of all, it should be decipherable, right? So one to achieve this one is the scope. What does it mean? No code should be the prefix of any other code assigned to a symbol. Suppose that if I say 0 as a for x1, x2 should not start with 0, right? So if that is the case, right, then we cannot say it is uniquely decipherable. We cannot say that it is prefix coding, right? So if it is a prefix coding, it's going to be uniquely decipherable, right? Need not be. It means that what I'm trying to say here is you can even have a uniquely decipherable code with prefix also, but the easiest way to get the decipherable code is to get to have what is called the prefix coding, right? So what you see here, right, this is, we need to have some bound, right? So how many bits we can assign for individual sample x1, x2, x3, and then x4. It means symbols. These symbols are, it is the combinations of here, right? So with length 1 or length 2, like this, something like that. This is with length 1, this is with length, and you can even have 1 0 which is of 2, right? And you can have something like 1 1 0, this is of n. This, I'm just saying this is an example, right? You can actually assign the symbol to the individual sample, right? So with length, for example, L1, and this one is L2, and right? You have that also this. So what is the average length bar? See, because it is a variable length, we call this variable coding. This is the variable length, right? So you would like to know as an average, what is that number of bits you are going to assign for the individual sample. This is what we call it as the average length. You would like to know what is that average length. The average length is divided by actual length assigned for the sample in corresponding probability. It is like 0.51 plus 0.5 L2 plus 0.125 L3, and then we have this L4. This is for elbow. To code way that this L bar, that average, right, per message or the, right. So this is a stage here available. So per sample, you wanted this average length to be minimum, right, minimized, right. So you wanted this value to be the minimum. So in that case, how to code it, right? In other words, what is length L1 and L2, we can actually assign, right, for the message, right? As you know already, you can understand that you have to assign list of bits or message with higher probability. If it is higher probability, say for example 0.5, you are going to assign very less number of bits. When the probability is less, here you are going to assign more number of bits. Then only this average bit exactly is the length I can assign, so that the coding is best. In other words, to know, right, for this, the efficiency, we can say that efficiency of coding, efficiency of coding, efficiency of coding, and what it is, what is that it related to, is what actually is noiseless code is actually giving you, right? So we will have a quick recap of what we discussed previous class to understand today's example problem, right? So we'll see the quick part. So we discussed about the inequality basically, right? So what is about? It is the bound for, right, is D, and with reference to what is the length of the code to that sample, right? So here in this case, you have x1, x2, xn. There are these samples available, and each sample is actually represented using what? D distinct symbols. So the previous example, the value of D is actually 2, right? So you are doing this. This is the case, right? Case, what is the understanding, right? The length of the code to the sample Li, that to be what? Li, right? So it is like, we have this x1, x2, and so on up to this xn, and we have this length of the code assigned, right? So to this, these things is given as what? To this L, right? So we have another definition. What is W? So this is W here. W is basically the number of samples coded with length 1. For example, let me again is x1, x2, x3, and then x4, right? And let me have this probability as 0.5, and this is probability 0.25, that the same combinations will take here 0.25 and this is going to be 0.25, and the bit this is 1, this one, let us say 0, 0, 0, followed by 1, and then 0, 1. So in this example, L1 is 1, L2, L3, 3, and 4 again 3. You have to understand the number of symbols, right, assigned to that particular page, right? That length is actually given here is length 1, and here is 2. So you have having 2 in this, and we have 3 here, so that is going to be in this, and then here 3 is there, and this is L4. And have another variable called W1. W1 is the number length 1. So how many are there? We have only one with 1. So W1 is 1 in this, and W2 is the number of messages with length 2. Again, it is going to be only 1. So you are going to have this W2 as 1 here, and then W3, the number of messages with length 3, you have 2 here. This is 1 here and this is 2 here. We have 2 in this. So W3 is actually 2 in this. So we have two different notations actually to represent this data representation what we have here. One is in terms of L, the another one is in terms of W. So what is that the equality is being you, right? So you are W1. W1 is as in the messages is 1, right? So you have in symbol. These symbols may not necessarily one, right? You can have a symbol like A, B, C, like this also, right? These are all the symbols, right? There are D symbols available in this. If you count, there are D available in this. So I can actually have a code like X1, X4, and so up to this Xn, right? I have a code like, I can A here, I can have B here, I can have here, like so these are all with length 1. This is length 1, this is length. I can make everything length 1. If that is the case, then the number of code, right, what we are going to have here for this message, right? So as I told you, there are D available. So the number of messages are to be D in this. That is not the case with all the example, right? Are not all to have what single length assigned. I mean the message. Suppose that I'm using EC for X1, X2, X3. Let's say with length 1. These all these 3 are length 1. These are all things with length 1. So that means that your W1 3 here, right? So what is the bound on this W1? That is the question. The maximum possible, because as we are having these symbols, the maximum is only D only. So in this, right, D is say 10 disks, right? A, B, C, that you are having 10 elements in it, right? So your W1 should be what? Definitely what, less than or equal to 10. That is 3 is less than or equal like this. It is over now. Now I'm going to look for this W2. How messages I can with length. The point here is, suppose if I want this and should not be the prefix. I mean, it should be the prefix code. It means that this box, you should not have A allowed, is allowed. These two are, of course, C is also not allowed because we already used it ABC, so it should not start ABC. So what are the remaining things we can have? That only we can put it here, right? So totally of D, right? We cannot use this D, so it is D minus 3. 3 is basically W1, right? So D is W1 choice only we are for filling this first. For filling this second box, you can choose A, B, C, anything, right? Is D. So you are having this here, right? So your W2 is bounded with this. W2 is getting bounded with what? D minus W1 into D, right? So it goes like this, right? So if you see equation for W3, right? So this is a maximum available for length 2. Now let us say that you are constructing the code with length 3. You can divide this one into 2 parts. This one with length 2, this one with length 1 here, right? So the maximum, this one here like this, D minus W, right? So we already used what? W2. So the remaining thing is here The remaining thing is D minus W1 into D minus W2, right? So that is in this two box together, right? And this box we can have D, right? So into D you are going to have. Now your W3 is bounded like this. If you keep on doing this, and actually keep on doing this, you get the expression which we already proved that it is ending up with a very nice expression. This is what we call it as this Kraft inequality. Here we have that expression in terms of what? W, not A. The same expression cannot happen in terms of Li. So that is what this both are same. This one with Li and this one with Wi's. You know what Wi and Li in that previous example, right? So this is what we call it as Kraft-Machmann inequality. Okay, fine. Now you are going to get a bound. We use this fact, right? Minus sigma I n pi log pi, that is less than or equal to minus sigma I equal to 1 to n pi log q. I hope this one I in the class, right? So now in of this we are going to replace it. We had that proof in the previous class.
Sir, we had.
Yeah. So now using this, right, to this qi, going to replace this qi as d minus l, right? The whole by what? Sigma equal to 1 to e power minus li. Just in place of qi substitute here, and if I simplify this, you get a very nice expression for this L bar. As I told you, L bar is the average length per message. That one you are getting it as what? Greater than or equal to h of x by of d. Very important expression what you are, right? So what does it mean? Your L bar always greater than h of x by LD log d. Suppose if I'm coding it in a way that L bar is exactly equal to h x by d, you have done a very good job. You have done coding. So we define the FNC as h of a or into what? D. This we can do, right? So when your h of x by d is exactly equal to L bar, you get FNC as 100%. We get as a 100%. Otherwise, you will always get lesser than that, right? Because L bar always going to be greater. So you have this bound, right? Now what we're going to do is we are specifically going to assign, right? Here, yeah, x1, x2, x, and then x4. Take only 4 here, right? So let me put like that. So let us say this is 0.5, this is 0.2, and this is this to be equal to minus log this corresponding probability. What is the value of this? This of 2 you can log 2 probability is what? 1 2 and here we get this, right? So it is minus 2. This is for minus. So or you get it as 1.
Sir, only till alpha is equals to.
Fine.
It's coming, sir, slowly.
Sir, yes, sir. There is a lag, sir, but it's coming.
Okay, okay, I think now what is seeing there? Are you able to see this L1 in this screen? The value
No, sir, only till neta is equals to
that you are
100%.
able to,
Yes, sir, now it came. Now it
you are
came.
not seeing after. What is
The one has got an answer.
what do you
L1.
one? Yeah, yes, yes, yes. Doing now here is I am is L1 purposeful for minus log P1. See, is L2 is minus log 2 P2. This purposefully I tell you the reason. L3 is minus log 3 P, right? And then is minus log. I'm sorry. So everything is based, right? And this P4, right? This is purposefully chosen. Can be this? What's the value of? What is the value of?
2.
Please
2.
tell. Type it. Type on the chat window. What is the value of L2? L2 is minus log. Yeah, that is 2 here. Good. What about
3, sir.
L4? They are good. Excellent. Lakshmi Saranya has, right? So this is perfect, right? If I'm choosing this one like this, and I am going to use now this, the number of sim D is going to here, say, right? So now what is happening is L bar is equal to h of x by log base 2 and number. So this is I mean 1. Let's calculate what is the value of h of x. So we have to calculate L bar as well as this h of x. That whole, that is what, right? So first let me calculate h of x, then we'll call it. Okay, first we'll call L bar. L bar. L bar, how will you calculate? It is very simple, right? You have a length multiplied with the corresponding probability, right? So it is 1 into what? 0.2 into five into plus 0.5 into, so this is the L bar. Someone calculate it. Now you calculate about this h of x. How this h of, you know, this average, right? It is the average in comparison, right? Minus sigma probability into log 2 this probability. It is like minus into what? Log 2.5 minus 0. Right? Log 2.25 minus 0.125 log 2.125 and then minus 0.125 into 0.125, right? So what is this value? You see that, right? I can bring here as minus this, right? This one, this minus I can bring it here, and I put this one. So I'll add the steps again. So that may be right. So what I am telling now is simplification of this one, right? As 0.5 into what? Log 2, 0.5 power minus 1, right? Plus, I'm using plus now, 0.25 up to 0. Power minus 1, and then plus 0.125 0.1 power minus 1, and then finally you have 0.125 up to 0.5 power minus 1. That what is that 0.5 power written as what? 1 by 2, right? 1 by 2 power minus 1, right? Is nothing but 2 here. Right? So the going to be what? 1 in this, right? I'm trying to say here, your value, this one is 1, and if I do here, right, 1 by, and 0.2 is what? 1 by 4, right? With 1 2 square, and that one you can make it minus 1. So that will 2 square is giving you the answer is what? And you, and this value similarly ends up with 3. What we are get is the your L bar and both are exactly same expression. So in that case, efficiency, you know that efficiency is h of x by L bar b log h of x is exactly equal to or you are getting right 1. Means 100% efficiency is what actually you are getting, right? So point what you have to understand is if L, the length of the code, you are choosing it as what? Minus log p, right? So it is like this now. If the length is chosen minus log, the probability you are ending up with 100% efficient coding. But why this is not, why we are not getting every time this 100%? The reason is we are taking this logarithm x2. We can that li, right? This li is integer. We want this the code to be the going to be the right. Suppose that by calculation, if this because of some arbitrary probability choose, and if this is coming as say for example 2.3, I cannot have 2. I can have a 2, not definitely what 3, and that reason getting that compromise, right? So in practice, actually using this li is my log to pi. We are actually li as having range minus to greater than point greater than that. I is this equal to sign here, right? So li should be greater than this because equal to also we have to put I plus equal to will put, because if it is coming as 2, then we can choose 2. There is no problem, right? We can choose 2, right? So suppose that L 2.3, right? Minus log minus 2.3, then this is going to 2.3, and you use a number between 2.3 to 3.3, and 2.3 plus 1 is 3. So you have to go for LI at 3 bits. Remember that we have for 3 bits and not the 2 bits. You should not round off. You should not round off. It should be greater than 2.3, and of course less than 3.3. 2.3 plus 1, right? 3.3. So you have to choose this LI to be 3 bits. So as you are having this length of the code, right? So it's coming as a we are this, and hence the efficiency is not always going to be what 100% in all the cases, right? So that is the bound given. Actually, that is what we say, that it is a noiseless coding theorem. What is the bound you are having? I told a little earlier, this is more general case. If the probability power minus Li, in other words, if Li is chosen, this is a more general statement. If Li is chosen as minus log pi, I told in the previous slide as Li is equal to what? Minus log pi, right? But now I'm telling it is a more general, minus log pi divided by log d. In the previous slide, I used d as 2, and this is log base 2, and that is becoming 1, and hence we got the expression as Li is equal to minus log pi in the previous slide. But in more general statement for this noiseless coding theorem involves this both, we use this d also, right? So your Li should satisfy this. Li is equal to minus log pi whole divided by log d, right? Of course, that's what I said here. Your Li should range between minus log pi by log d to minus log pi by log d. Here, please change that. Plus 1 is missing, right? So it is like that. So take the product and the summation with pi, right? So what I'm trying to say here is you multiply pi on both sides, here also, and take the summation over I equal to 1 to n in a case, sigma I equal to 1 to n here, and this is also sigma I equal to 1 to n here, and this is also sigma I equal to 1 to n here. In all the case, if I do, what is that you get? This one, what is that? Numerical quotient. So that is your h of x by the denominator log d is missing here, and what you see in that middle one is sigma equal to 1 and pi. So this one I write it as clearly here. This is sigma I equal to pi li, right? So that is nothing but your L bar. So that is given here, L bar. And coming to this expression, h of and divided d, which is missing here, and in all values probability, that one, that is the reason you are getting this one here. So this x, that it is a noiseless coding, that bound for the advent of your message, which is bounded between h of x log d to h of x by log d plus 1. So this is a very important equation, right? You can go for the coding, do that. Just screen now. Are you able to see the screen?
Yes, sir.
Okay. There are two ways. One is the Huffman code Fano coding, right? So let us consider this x1, x2, x3, then x4, right? And probability assigned to that is, let us say that it is 0.5 and this is 0.25, and we have here 0.125, right? Say this is 0.0625, right? Okay. Okay, let me take one more 0.125. So this is becoming 0.25, right? So it is over. Okay. And the fifth one is 0.0625. When you add this, you should get 1. Are you getting 0.5, 0.75 is coming. This is 0.25, this is 0.25, it is ending up with 0.25, and then it is 1 only, right? So this is the probability given to you. How to code it? What you have to do now, I am going to tell the technique for Huffman coding. It is very important. Listen carefully, right? So what I am going to do is, I am going to combine these two symbols, and the total probability I am looking for, that is coming as what? 0.125. So I have to bring to the location just above where this point, right, 125 is greater than the existing probability. It means that this is like this. When you do this summation, you are getting this as 0.125. This 0.125 is coming as it is. Let that one I am putting as it is here, and this one 0.25 I am putting here, and this 0.5 I am writing it here like this, right? So in the next stage, again I am combining these two. You are getting this as 0.25. I'm just bringing to the location just above this 0.25 here, right? So this 0.25 is coming as it is, right? And this 0.25, when you add these two, you are getting this. This one is coming as it is. This is 0.5 here. This is a third stage. And then, as usual, you are going to combine these two and then bring to this top here as 0.5, and this one as 0.5 here. And finally, you are combining, you are getting that as 1. Now what you do, 1 or 0, that is up to you. Let me take 1 0 here. This is 1 0 here, and this place as 1 0 here, right? Okay, I'll use a different color for this so that you can understand better, right? This is 1 0 here, and this place is also 1 0. Wherever you see this partition, no, you have to put this 1 0, and this is 1 0 here. Now it is a time to code it. X1, what is the code you are going to do? You have to see to that line where this x1 is going all the way, right? So it is actually 0 in this, right? So you have to put that 0 here. Then coming to this x2, you have to track where this x2 is moving. This arrow is there, and then it goes this arrow, right? And it goes like this, So it ends up with 2 regions. See that this is x2, it goes like this, right? So it crosses this one and it crosses this one, right? So it is like that, 0 and 1 is there. What should I write? 0 1 or 1 0? I'll write it 0 1 or 1 0. Which is right? Type it on the chat window. Which is right? You have, I'm saying 0 1 1 0. Excellent, excellent. The reason is it should be the prefix, right? It should be the prefix. So you have to put it as 1 0, right? You are right. Then what about x3? X3 again you have to trace, right? This is 0 in this point, this location, and then it goes in this way. This is 1 here, and then combining here it is 1 here. So what is that answer? So this is going to be, somebody type on that, it is 1 1 0. So what about x4? X4 is here, it starts 1 and then it goes here 1. Yeah, 1 1 1 0. Excellent. X5 it is what? X4 is it 1 1 1 0 or what? 1 here, 1 here, 1 here. No, X4 is 1 1. Okay, and X5 is this one, right? 0 here, 1 here, 1 here, 1 here. So that is going to be what? 1 1 1 0. This is that final 0 is coming into picture, right? So this is the way how we have to code. This is using this Huffman coding. Your length L1 is 1 in this, and length L2 is here 2, L3 is 3 here, L4 is 4 here, and L5 is again 4 here, right? So you are actually using length 1, length 2. It's a variable length coding. Your image data, right? Whatever you are having, your JPEG compression, right? Where it is, where you are saying that, yeah, you can actually interchange. In place of 1 0, you can actually totally you can revert. You can put 0 1 0 1 0 1 0 1. If I put 0 1 here, I have to put 0 1 here. I have to put 0 1 here, put 0 1 here, or you have to put 1 0 1 0 1 0 1, right? So that is only the representation. So you can actually either use 1 0 or 0 1, but it should be consistent. You have to use the same set of pair here in every partition. It should be like that, right? So now we can actually calculate this L bar, and then we can calculate this H of X. L bar is what? What is the value of L bar? Probability, right? So L is what? 0.5 into 1 plus 0.25 into 2, 0.125 into 3 plus 5 into 4 plus 0.0625 into 4. So what is the value of this? Somebody tell me that. And what is that H of X? H of X is what? Probability into that log probability with what? Minus sign. Minus 0.5 log to 0.5 yeah. You are asking this L bar, right? Vikash Kumar, you are asking L bar, isn't it? Is it?
Sir, I'm asking about X1, X2.
X1, X2.
Yes, sir.
I don't understand. You want me to explain about this coding?
Yes, sir. And how can that X1, X2 value 0, 1, 0, H5?
How to get this code, right? You are asking how to get this code, right?
Yes, sir. Yes, sir. Yes.
Yeah. So what you have to do is you have to trace. For example, let me take X3. You have to trace here. If you trace this, you have to see that arrow mark, right? It comes 0 here, right? And then you have to trace like this. It goes it in that way. You have to see what is this. This is 1 here. Again, you have to trace here. So you are getting it as 1, right? So 1, 1, then what? 0, right? You understood the point? You have to see that arrow mark where it goes. This arrow mark goes here where we are getting 0, and then it goes like this. It comes to this point as 1, and then here it goes like this and it is coming as 1. So now you are doing it the reverse way. This is 1 here, this is 1 here, and this is 0 here, and that is the code we are going to assign for x3. Are you getting now?
But sir, x4 and x5 value we can do exchange now.
Interchange means what? They are EQ probable, right? So we can actually have 0, 1 also, no problem in that. You can have it, that is not a problem. You can have it, but you see in this case these two probabilities are equal. You see that this is 0.0625, this is also 0.0625. In that case, that is not going to affect more. But to make it as a more general way to do this, it is important that you have to put 1 at the top and 0 at the bottom. 1 0 here, 1 0 here, and I'm using 1 0 here. That is important, right? But interchanging this x4 and x5 you can always do, because they are all with what? EQ probable. In fact, you have to understand that the symbols whatever I have arranged here, they are in the descending order. It is very important. Very good, actually, because you asked this question. I think I didn't say explicitly this. It should be in descending order. Your symbols, right? So if you are given some other probabilities, you have to arrange the symbols here, message, in descending order of what? Probability. That is very important. You have to arrange them in a descending order: 0.5, 0.25, 0.125, and this one. And these two are EQ probable. So you can have an interchange. x5 and x4 is always, you can do it. And x3 and x2, you can actually do the interchange. You can do that interchange. There is no problem. x2 here and x3 here, and then x4 here and x5 here, we can actually do here, right? Because they are of EQ probable, so you can actually do that. So to answer your question, you can, for this particular case, yeah, the code 1111, 1110, we can actually interchange for x4 and x5. That doesn't matter, because they are of EQ probable. When they are EQ probable, there is no problem in it. Is that all right now?
Okay, sir.
Yeah, so I let me finish off today's class with this. We'll continue this Shannon-Fana coding. Once again, we will do this Huffman coding in the next class, right? So before coming to this next class, I wanted you to calculate this h of x and L bar. Let me start with that, right? So I have not completed here. I wanted value for this L bar, h of x, and of course, log d. Log d is going to be 1 because d is 2. D is 2, right? So this is 1 here. And finally, I want that answer of for this expression h of x, d is 2 here, right? H of x by L bar log d. This is what I wanted, right? I want this answer to be given in the next class. Somebody has given that value of h of x. Good. L bar also 2.65. Excellent. So that the you just cross check it. Anyhow, we'll check in the next class, right? As Nishit Mangal has written, you get this as 100% in the next class. We'll stop here. Is that all right?